welcome friends in this class. In the previous class we have discussed about the fixed endpoint problem. We are trying to find out the optimal value of a given functional subjected to the endpoints are fixed. Today we will see the another problem which we can say the free terminal point problem, in which T0 is fixed or the initial point is fixed, but the final point is free with respect to the time and with respect to the x. So, both x and t we will consider to be the free, then we will see the different cases which can arise in such a problem. So, we will have a free terminal point problem . So, we can define T0 and x T0, value of the x at the T0 is fixed. I define this my optimal trajectory x star, and this is the variation x t can be simply written as x star t plus delta x of t. My optimal trajectory is terminating at TF point, and say the trajectory will go beyond the TF point, TF plus delta TF. At TF point, let my optimal trajectory will have value xf so the problem is to find the optimal value of J, my performance index, which is simply defined as T0 to TF V x, or in more general form we can write it as like J of x t, V of x t, x dot of t, t dt if x t0 x0 and t0 is fixed and xtf tf is free. So, this is our problem. We have to find the optimal value of the j if my boundary conditions x t0 x0 and t0 is fixed XTF, TF is free. So, basic approach to solve this problem is same as we have discussed for the fixed endpoint problem. Means first of all we will find out the increment. From this increment we will write the first variation as per the fundamental theorem. First variation must be equal to 0. From there we will get the conditions for this V to be optimal for the given boundary conditions. So, our first step is to find out the increment. How we define the increment? Delta j is nothing but the value of the j at x t, x dot of t, t minus value of the j at x star of t, x dot star of t, t. What is x t in this case? This is x star plus, or in other way I can also write this as x star of t plus delta x of t, x dot star of t plus delta x dot of t. At delta x is there, so my t is nothing but t minus j. I am dropping the t, x star, x dot star, t. So, this j star is I can directly write, because in this case my t is varying from t0 to tf, but once I am writing j for x star plus delta xt, my time is varying from t0 to tf plus delta tf. So, this can be written as integral t0 to tf plus delta tf v x x dot t. Here x is x star plus delta x. So, I am simply writing the v, this into dt minus for j star j x star, this is t0 to tf v x star x dot star and t dt. So, this equation gives me the increment in j, which we can find. So, my increment is delta j is given by this equation. So, now in the next what we are doing, here we have the integral limit from t0 to tf plus delta tf. This we will break in t0 to tf and then tf to tf plus delta tf. So, this integral we are breaking into the two integral. The first integral we can club with the second one, because both will be from t0 to tf, or I can write my delta j as t0 to tf v x x dot t minus, I am writing for this v x star x dot star t dt plus the breakup of this from tf to tf plus delta TF V x dot t dt. Now, if you will see, this is the first integral is similar to what we will have in our the fixed endpoint problem. So, this we will say, let us say my first integral give me the delta j1 and the second integral give me the delta j2. So, first we will take, so my delta j I am simply writing as delta j1 plus delta j2. So, we will treat each term independently. Let us say delta j1 is given as my T0 to Tf. So, this V x dot t minus V x star dot t dt, because this x is nothing but my x star plus delta x. So, expanding this term using Taylor series, what we will get? So, delta j1 T0 to Tf, we are simply going to get V x star dot t plus del V. Now, all V is the function of x star x dot star t by del V by del x obtained at optimal point into delta x plus del V by del x dot. I am writing the dot here simply because I have the same value into delta x dot plus higher order term minus V x star x dot star t dt. So, these two terms will get cancelled out and we are left with del V by del x delta x plus del V by del x dot delta x dot plus some higher order terms into dt. So, if you will see for J1 I will get the same expression as we are getting in the fixed endpoint problem. So, delta J1 I can represent it by this. So, now in this case if I will expand this term using integration by part, expanding T0 to Tf del V by del x dot delta x dot dt using integral by parts. So, this second term gives us, so we will get plus del V by del x dot into delta xt T0 to Tf. As my initial point T0 is fixed, so delta xt0 will be 0 and this term means I have to evaluate only at the point Tf. So, this second term T0 to Tf del V by del x dot delta x dot dt can be written as minus T0 to Tf d by dt del V by del x dot delta xt plus del V at x of Tf, x dot of Tf, Tf by delta x dot into delta x of Tf. So, this will be the second term which we are expanding. So, in J1 expression, if I will club this, so the total J1 expression I can write as so delta J1 can be written as T0 to Tf del V by del x minus d by dt del V by del x dot delta xt dt plus higher order terms plus del V So, this the value of the V by del x dot, and this whole is evaluated at T f point multiplied delta x of T f. So, the first delta j we have divided into the two terms J 1 and J 2. So, delta J 1 can be written as given by this last expression. So, the J 1 we have written by this. Now, next we will see how we can write the second integral. This we will keep with us, the last part. So, what we have taken as the J 2? So, delta J 2 is considered as, this is my integral from T f to T f plus delta T f V x x dot t dt. What actually this integral represent here? Say, to find this value, let us see this. We are integrating from the time T f to T f plus delta T f, and V is x is my x plus delta x. So, this means x plus delta x at T f point is this, T f plus delta T f point is this. So, I can say this is nothing but area under this curve. So, we can recall that the delta J 2 we are representing as T f to T f plus delta T f V of x x dot t dt. So, what this integral represent here? My limit is from T f to T f plus delta T f, and the V value which is dependent on the x, which is x t x star delta t to this. So, at this point the value of the x will be the x star of T f. So, this integral is nothing but the area under this curve, and area under this curve can be simply represented as V x star of at the point T f x dot of T f into delta T f plus some higher order terms. Sorry. So, this is x of T f, x dot of T f, delta x of T f. At T f point, we will have the variation into this. So, this can be approximated as V x star of T f plus delta x of T f x dot star of T f plus delta x dot of T f. So, this can be written by as given here. Now, expanding this with Taylor series, what we can write for the J2? This is V x star of Tf, x dot star of Tf, Tf multiplied with delta Tf, which I have missed here, delta Tf. So, this is the first term plus del V by del x evaluated at the Tf point into delta x of Tf, delta x of Tf multiplied with delta Tf plus del V by del x dot evaluated at the Tf point delta x dot of Tf delta Tf plus what is my higher order terms and multiplied with delta Tf. So, if we will see in this, delta V multiplied with delta Tf is the only first order term here. All other terms are the second order and the higher. So, these can be approximated to 0, this can be approximated to 0, or we can neglect these, this can be approximated to 0. So, delta J2 simply can be represented as V x star of Tf, x dot star of Tf and Tf. So, we have evaluated the delta J1 and delta J2. Okay, today in this lecture we stop here. In the next lecture we will derive the complete expression for the J and complete our free endpoint problem in the next class.